This is lecture 8, where we'll be looking at the impulse response of systems. And in particular, we'll be looking at LTI systems. LTI stands for linear time invariant. So we're looking at a particular type of system, a linear time invariant system. And we're going to be looking at something called the impulse response. So just as a reminder of where we are, we're now at lecture 8, so we're very close to the end of the semester, so we only have 11 lectures in total. So this latter half of the module is where we look at systems. So last week we spoke about system classification or system characterization, and now we're looking at how we describe systems. How do systems actually behave? So we're going to look at the behavior of systems, and in particular we'll look at something called their response or their impulse response. And that will help us next week understand how the Laplace transform can simplify this. And then in the final 2 weeks, we'll look at the Z transform, which is for discrete time systems. So the Laplace transform is for continuous time. So just to recap from last week. Last week we spoke about how to classify systems. We spoke about linearity, we spoke about causality, we spoke about time invariance, we spoke about memory, static versus dynamic, and we spoke about invertibility. And we gave criteria for some of these. So linearity, we gave a test for linearity, and we said for a system to be linear, it needs to be both additive and homogeneous. And we described in detail what each of these means. Homogeneous, or the property of homogeneity, is often referred to as scaling. So scaling or scalable is the adjective. We spoke about a causal system. It's a system that doesn't anticipate a future input. We spoke about a TI, or a time invariant system, a system whose behavior doesn't depend on time. We spoke about a static system, a system without memory. So that means a system that doesn't depend on a future value or a past value. It only depends on the current, present value of input. We spoke about an invertible system where it's possible to recover the input from the output. And we did a double Kahoot class and a problem sheet. And on Monday, you will have your next class test. We'll also look at problem sheet 8. So today we're going to look at something called the impulse response. And in particular, we're talking about linear time invariant systems. And we're going to talk about some of the properties of these linear time invariant systems. So whenever you see LTI, that means linear time invariant. Okay, so most of the systems that we like to use in our engineering systems are LTI systems. We'll also introduce something called the step response and a ramp response. So it's a similar concept to impulse response, but we'll take it one step further to step and ramp response. So it's not a long lecture, it's quite brief, but quite a few simple but very valuable concepts. So just as a reminder where we are, this is where we are here. You have another 2 weeks until test 5. So test 5 will be on the 14th of December. So by the time you listen to this lecture, you will probably already have sat test 4. So the next test is scheduled for the 14th of December, and that'll cover lectures 8 and 9. So impulse response and Laplace transform. Okay, so these two lectures will go into the next class test. So what do we mean by impulse response? Now, what I'm going to say next is really a summary of almost all of this lecture. The impulse response is exactly what it sounds like. The impulse response is the response, and response just means output. That's what response means. It's the output when a unit impulse is applied to the input. So the impulse response is the output when a unit impulse is applied to the input. So this is my system. We represent it using a block. So it's a linear time invariant system. This arrow on the left, that's the input. The arrow on the right, that's the output. We generally use x of t for the input and y of t for the output. In this slide, I've simply illustrated the input as a unit impulse. Why? Because that's what it is. That's the definition. The definition is, if I were to apply a unit impulse at the input, then whatever comes out the other end, I call the impulse response. So the definition of the impulse response is the output of an LTI system when the input is a unit impulse. Why is this important? Because we can define an LTI system completely using this impulse response. That means if I know how this system behaves when an impulse is applied to it, it means I will know how this system will behave when any signal is applied to it. So if I were to apply any signal to the input, I can find the output as long as I know the impulse response. Now, in terms of notation, we will use h of t to represent the impulse response. So h of t is the impulse response. Different textbooks, different websites might use different notation. In this module, we'll use h of t to represent the impulse response. So that's 80% of today's lecture finished. That definition really summarizes almost the entire lecture. So take this as an example. A system has an impulse response given as e to the power minus 2t times u of t. So the impulse response is a decaying exponential. Okay, so this is h of t. What does that mean? It means that if you were to apply a unit impulse to the input of a system, this is what you would get at the other end. This is the output you'd get. Now the question says, what is the output of the system if the input is a unit impulse? So that's almost a trick question. If the input is an impulse, then the output is h of t, by definition. So that is my answer Why? Because that's what we're told in the question. We're told that the impulse response is that. So therefore, if you apply an impulse at the input, what do you get? You get that. You don't get an impulse, you don't get that, and you don't get that. You get exactly h of t. All right, so h of t is y of t. So the output is the impulse response. So the output is h of t by definition. Okay, so you might think this is a really silly question. I'm stressing it because once you get this, once this makes sense to you, many other things will become almost obvious. Okay. I just said 2 slides ago that knowing the impulse response, you can completely describe a system. That means you can find the output for any input. So this is my system. If I apply an impulse to the input, the output is the impulse response. Anything new here? No, this is, if you like, the definition. So nothing new. But what is new is knowing this, I can find the output to any input. Any input. So this time, look what I've got. Same system, nothing's changed, same system, but my input is something else. What's my input? It can be anything. It could be a signal like that. What's the output? Well, it's not going to be h of t because h of t only happens when you have an impulse. This isn't an impulse. But what you do get is the convolution of the impulse response with the input. So this is convolved with the impulse response to give you the output. So this is really, really useful. It means we can find the output to any input by simply carrying out a convolution. Quick question. If I have a system with an input x equals delta t, that means a unit impulse. All right, so that's my input. And the output is this much. It's a one-sided exponential. So my input is an impulse, and my output is, it's an exponential multiplied by cosine u of t. So that'll probably look like something like this. Okay? It doesn't matter what it looks like. This is y of t. This is the output when the input is an impulse. What is the impulse response? Again, the impulse response, by definition, it's the response, output, when an impulse is at the input. And here the input is an impulse. We're told that the input is an impulse. So therefore, this is the impulse response. So the impulse response is y of t, again, by definition. So if you've been following, you'll probably find this question really silly. Particularly, I have only given you 2 choices. It's the silliest question ever, but I'm trying to stress this point, that the impulse response, sometimes you don't need to do any work to find it. It's simply the output when the input is an impulse. And this is exactly the same as that. So that is your answer. Okay, so now we're going to start looking at the same idea in a few different ways. We're going to look at some properties. But first of all, let's look at it in the frequency domain. Remember a few slides ago I said to find the output for any arbitrary input x of t, you need to carry out the convolution of x of t with h of t. Well, convolution in the time domain, what does that correspond to in the frequency domain? It's simply multiplication. So if I take my input in the time domain and I convolve it with the impulse response, remember h of t is my impulse response, that will give me my output y of t. So the output is the input convolved, that's the convolution integral, with the impulse response. Now in the frequency domain, same thing. The output can be a function of omega, x can be a function of omega, and h can be a function of omega. Now h of omega, we don't call that the impulse response. We'll talk about that soon. But x of omega is the input. But the difference now is we've converted the convolution to an integration, the convolution to a multiplication. So we can multiply in frequency instead of convolving in time. And this is simply to show you that when you carry out the convolution integration, it doesn't matter which way round. So you could write it as h of t convolved with x of t, or x of t convolved with h of t. It's the same. Now let's take an example. We're asked now to find the impulse response of a system that's being described using an expression that links the output to the input. So this looks like a delay. So the output is equal to the input after delaying by 1 second. So this system is a unit delay. There's a 1 second delay. The output is equal to the input 1 second ago. The question is, what's the impulse response? Now don't try to do anything clever. The answer is really simple. Apply the definition. The definition is the impulse response is the output when the input is a unit impulse. The input needs to be a unit impulse. So we just replace the input, x, with a unit impulse. So the impulse response is the output when the input, x, is a unit impulse. So there, we've answered it. That's the answer. That is the impulse response. The impulse response is delta of t minus 1. So that is the impulse response. We found it simply by applying the definition. Next example, very similar, but this time it's not a simple delay. Here it's a delayed version of x plus a scaled and further delayed version of x. So the output at any point in time t is equal to the input 1 second ago plus twice the input 3 seconds ago. And again, the question is, find the impulse response. So that should read, find the impulse response. So what's the impulse response? By definition, it's the output when the input is a unit impulse. So I'll replace the input with a unit impulse. And I'll replace y with h. And there we have it. That is my impulse response. So simply by applying the definition, by applying our understanding of the definition, we can find the impulse response to a system that's described in such a way. One more example. Now we're going to look at this example in two ways. We'll look at it once now, and we'll look at it in a few minutes' time. So the question says, a unit impulse is applied to the system, and the output is that. All right, so at the input to a system, we have a unit impulse, delta, and that's the output. Part A, find the impulse response, h of t. Now you're probably fed up of this question that keeps repeating itself. What is the impulse response? Well, the impulse response is given right there. By definition, it's the output when the input is an impulse, and that is an impulse, so therefore that is my impulse response. So it's h of t equals 3t u of t. Okay. The second part says find the step response. So you can probably guess what the step response means. The step response, and we call this S of t generally. Some books will differ, but in this module we'll use S of t to represent the step response. So the step response is the output response when the input is a step. So if the input is a step function, the output is called the step response. So this is the step response. Now remember we said we can find the output by carrying out a convolution between the input and the impulse response. So the output, or here I can call it S of t, is a convolution of x of t and h of t. Remember convolution integration? So you can carry out that integration, then substitute the limits. What's happened to the limits? Why has it changed from minus infinity to infinity to 0 to t? It's because we have this unit step. Okay, so you've got the 0 here, and you've got the t here. So from 0 to t. If you carry out the integration, that becomes t tau minus tau squared over 2. Remember, the variable if the integration isn't t, it's tau. So you end up with that expression there. So that is what we call the step response. That means that if a unit step was applied to my input, that's the output I would get. So can you see how the impulse response is really useful? Because I've used it. I've used it right there. So without the impulse response, I wouldn't have been able to find the step response. Now we'll answer this question again in a simpler way in a few minutes, but this is how we would use the convolution integration to answer a question like this. Now remember last week we spoke about something called a causal system. We said a causal system cannot anticipate a future input. So if you just think about what implication that has on the impulse response of an LTI system. Say there was an impulse applied at t equals 0. If the system cannot anticipate future inputs, that means that the earliest the system can respond is t equals 0. It cannot respond before t equals 0, because if it were to respond before t equals 0, it would be anticipating a future input. So we say the system cannot respond before t equals 0 because the input is applied at t equals 0. So it can't respond before t equals 0. What does that tell you about the impulse response? It means the impulse response has to be 0 for t less than 0. It must be 0. This cannot be anything other than 0 if the system is to be causal. If the system were to respond, to respond at, for example, t equals -4, even though the input is applied at t equals 0, then it would be a non-causal system. It means the output is happening before the input. This is 4 seconds in the future. So when this happens, this is still in the future. So that would be non-causal. That would be anticipating future values. That is not possible. So I'm going to rub all that out. So this is an important characteristic of a causal system. The impulse response for a causal system is 0 for t is less than 0. And another one of these silly questions. So if this was a lecture, this kind of question would be there to check if you were paying attention and to see whether or not I managed to make that point clearly. But I'll go through it nevertheless. A causal system cannot anticipate future inputs. So what does this tell us about the impulse response of a causal system? Well, we just said it means h of t needs to be 0 for all t less than 0. That is for a causal system. Another example. This time we're actually being told that the input is an impulse. And the output is this. That's the same as telling me that the impulse response is that. Okay, so I can simply say the output is the impulse response. So h of t equals y of t. Why? Because x of t happens to be a unit impulse. Okay, so that's not what the question is about, and that's not particularly clever. That's really obvious. The question is asking, is the system causal? Now, don't ask yourself, is this greater than that? Ask yourself, is h of t 0 for t less than 0? That's what you need to ask yourself. Now, h of t here looks like something like this. It's a product of 3 things: an exponential, a cosine, and a unit step. And most importantly, the unit step starts at, if we do it the long way, it starts at t equals -2. So the unit step starts there. So your impulse response will look something like oops, this, and then 0. So if you look at that, we ask ourselves, is h of t 0 for t less than 0? Well, this is t less than 0, and h of t is very much not 0. Right? So I'll highlight the bit I'm not happy about. This bit isn't 0. So it isn't causal. For it to be causal, we wouldn't have this bit. So h of t would have to be 0 for all negative time. The fact that we have this means that the signal would be responding before the input. Because remember, the input is a unit impulse at t equals 0. The input is happening at this time here, t equals 0. That's the time where the input happens. The input happens here. How can the system respond before the input? It can only do that if it's non-causal. The next definition I want to share with you is for something called a relaxed system. So a relaxed system is a causal system that has 0 input initially. That means the output at t equals 0 is 0. So sometimes we say a system initially at rest. So when reading questions, sometimes it'll say a system initially at rest, meaning initially at at t equals 0, y will be equal to 0. So if a system is initially at rest and it's causal, we call it a relaxed system. And you can assume that all LTI systems are relaxed. If ever a system isn't relaxed, if it isn't at rest, you'll be told in the question. So it's a safe assumption that all LTI systems are relaxed. Okay, now we've spoken about an impulse response. We've sort of introduced something called a step response. Now we'll talk about something called a ramp response. And you can probably guess, if the impulse response is the output when the input is an impulse, a step response will be the output when the input is a unit step, and a ramp response is the output when the input is a unit ramp. Okay, so that's straightforward. Maybe less straightforward is how can you find the step response from the input response, and how can you find the ramp response from the step response? Well, it turns out if you take the derivative of the impulse response, so if you take the derivative of the step response, you get the impulse response. And if you take the derivative of the ramp response, you get the step response. The other way around, you can say the integral of the impulse response is the step response, and the integral of the step response is the ramp response. This is exactly the same slide. I've simply illustrated it this time. So if I have a system and I apply a unit impulse to the input, the output is the impulse response. Okay, so this is what we've been talking about for the last 20 minutes. Now, if my input isn't an impulse, if it's a step, then the output's called the step response. And if the input is a ramp, then the output is the ramp response. Now, notice that the unit step is actually the integral of a unit ramp. Sorry, of a unit impulse. And a unit ramp is the integral of a unit step. So each is the integral of the one before. In the same way, the ramp response is the integral of the step response, and the step response is the integral of the impulse response. So there you have h of t, here you have h of t, and here you have s of t. So impulse response, so impulse on the input, impulse response on the output. Unit step on the input, step response on the output. This is the integral of that. Similarly, this is the integral of that. If you have a ramp at the input, you have a ramp at the output, or a ramp response at the output. A ramp is the integral of a unit step, and the ramp response is the integral of the step response. So that's handy to know. In the same way, I mean, if this is the integral of that, then this is the derivative of that. And similarly, this is the derivative of that. And again, this is the derivative of that, and this is the derivative of that. So, remember example 3? It was that silly example where I gave you an impulse at the input, and I asked you for the impulse response, and that was obvious. But then I said, what's the step response? And we had to do a convolution. We said, oh, the S of t is x of t convolved with h of t. And it was that nasty integration. Well, now I don't need to do that, because now we've learnt that the step response is the integral of the impulse response. So I can simply integrate the impulse response. So there's my impulse response. Integrate it. Remember, you're using the variable tau. So in one step, you get the same result. Okay, so much less work, simply by recognizing that the step response is actually the integral of the impulse response. A few more slides to go. If you have an impulse applied to an LTI system, the output is called the impulse response. That's the definition that I keep banging on about, okay? So if I have this impulse, I have some output, that's my impulse response, okay? Now, if I delay my input, if my input is delayed by tau seconds, because I have a time invariant system, the response will also be delayed. I have a delayed impulse response. So the delay that happened here will cause a delay there. So that's an important property of a linear or of a time invariant system. So there's nothing new in this slide, but it's just to show you that if you delay your input, it will also delay the impulse response. So there are more properties. The first one is always the obvious one. Impulse at the input, impulse response at the output. So delta at the input, h at the output. Now, if I were to scale my input, so it's no longer a unit impulse, it's a unit impulse multiplied by b, what would that do? It would simply scale my impulse response. Why is that? It's because of this word here, linear. Okay, so it's a linear time invariant system. Remember? LTI. So the L stands for linear. Linear, remember, has two things. It means additive and homogeneous or scalable. So therefore, if I were to multiply by something, if I were to scale it, the impulse response would also be scaled. If I were to delay, it would also be delayed. That's the previous slide, time invariance. So that's what we spoke about just there, the delay. Now, what if I don't have one impulse, but I have two? So an impulse at t equals 0 and another impulse at t equals a delayed impulse. Remember we said it's linear, therefore it's additive. So if I add, notice that addition, that's my addition. If you're adding at the input, because it's a linear system, the outputs will also have that same addition. That means you can add the two responses. So you'll have h of t plus h of t minus a. Where did the t minus a come from? It came from the time invariance. Where did the plus come from? It came from the additive. Now just a couple more things and we'll have finished this lecture. This is just a quick example. We're told that a system has an impulse response of 3 times delta t. That's the impulse response. The question is, what would the output be if the input was 2 times delta t? Well, first of all, we need to find the... well, actually, we don't need to do much work at all. This is really easy because we're told the impulse response, that's the output if the system had a unit impulse at the input. So if the input was a simple delta, the output would be 3 delta. Where did I get that from? From there. So by definition, if the input is an impulse, that's the output. All right, so let me just label that. This is the input equals impulse, a unit impulse. The output is h of t by definition. Now the question isn't that. The question is asking, what would the output be if we actually had a 2 right there? Well, using scaling, because of linearity, it would simply be 2 times that. So if you multiply the input by 2, you multiply the output by 2. So this would be your answer. One more example. Same thing. I'm given the impulse response. So let's draw my system. The impulse response is 3 delta t. So that means if my input is delta, if that's my input, that's my output. Why? By definition. That's what h of t means. The question is, what would the output be if the input was 2 delta t minus 5? So that's my input. What's the output? So notice 2 things are happening. First, I'm multiplying by 2. There's no 2 here. Second, I'm delaying by 5 seconds. So using the time invariance and linearity, you'd expect the y to be equal to 2 times 3 times delta of t minus 5. So you'd have the 2 and the minus 5. So the linearity happening there and the time invariance happening there. So that's your answer right there. So last thing for today's lecture is what happens when we cascade LTI systems. What do I mean by cascading LTI systems? It means arranging more than one LTI system such that the input for one is the output of the other. So one feeds into the other. So this is called a cascaded system. So if the input is X, the output of the first system is the convolution of X and H, or the convolution of X and H1. Now, if that is fed as an input into the second system, the output will be the convolution of this input with the new impulse response, H2. Now, if you switch the order of these two systems, because they're cascaded, this time you'll have the convolution of X and H2, that's your X and H2, and that will be convolved with H1. But because this is a convolution operation, they are the same. Okay? These are exactly the same. So it doesn't matter which way around you arrange your cascaded system. They can be implemented in any order. So that's the end of lecture 8. What have we learnt today? We've learnt the definition of the impulse response. We've said it's the output when the input is a unit impulse. We've also introduced something called a step response and a ramp response. And we've described how these three are related by integration or differentiation. We've also said that the output of an LTI system is the convolution of the input and the impulse response. We've given a criterion for something called a causal system. So we already know that a causal system cannot anticipate a future input, but this time we've actually written that as a condition, that the impulse response has to be 0 for negative time. We've also learned that cascaded systems can be implemented in any order. All of these things will be very useful as we move forward. So next week we'll be looking at the Laplace transform. So the Laplace transform will enable us to look at systems or continuous time systems in a different domain. So that will be next week, and then the week after, on the 14th of December, you have your class test. So make a note of that in your diary. I hope you found that helpful. So until we meet again on Monday, Thursday, or Friday, stay safe.